In an extremely clean space, humanity is conducting the most precise manufacturing. This is a semiconductor wafer fabrication facility, also called Wafer Fab or Fab. Here, engineers transform ordinary silicon crystals into the foundation of modern civilization, chips. The entire process requires hundreds of procedures. Each step demands nanometer-level precision. 1 nanometer equals 100,000th of a hair diameter. At this scale, even a single dust particle becomes fatal contamination. Let us enter this ultra-clean world, observing how silicon wafers step by step become chips. In this process, time seems to slow down. Every movement requires ultimate patience and precision. Semiconductor manufacturing begins with a piece of pure silicon. This silicon's purity requirement reaches 99.9999999%, the so-called 11 nines. This means among 10 million atoms, only one impurity atom is allowed. This is one of the purest materials humanity can manufacture. Silicon ingot growth uses Czochralski method. This process occurs in a quartz crucible. The crucible contains molten silicon liquid with temperature maintained at 1420 degrees Celsius. This temperature is exactly 6 degrees above silicon's melting point of 1414 degrees Celsius. A seed crystal is slowly immersed into molten silicon liquid. Seed crystal is a small silicon rod already possessing perfect crystal structure with diameter approximately 10 millimeters and length of 100 millimeters. Seed crystals' crystal orientation must be precise. Typically 100 orientation is used, meaning crystal surface is parallel to specific face of cubic lattice. After seed crystal contacts silicon liquid, it begins slowly pulling upward. Pulling speed is extremely slow, only several millimeters per hour. Simultaneously, seed crystal rotates at 10 to 20 revolutions per minute. Rotation purpose is distributing newly solidified silicon uniformly, maintaining cylindrical shape. As seed crystal pulls upward, silicon liquid solidifies at seed crystal bottom, forming monocrystalline silicon. Solidification process must be extremely slow and uniform. Any speed fluctuation creates defects in crystal. Entire growth process lasts dozens of hours, ultimately forming silicon ingot with diameter of 300 millimeters and length of 2 meters. Silicon ingot weight is approximately 150 kilograms. This huge monocrystalline silicon rod has every silicon atom internally arranged orderly, forming perfect lattice structure. Under microscope observation, this regularity extends to atomic level and visible to naked eye. Grown silicon ingot requires annealing treatment. Annealing temperature is 1000 degrees Celsius with duration of 24 hours. This process purpose is eliminating internal thermal stress in silicon ingot, stabilizing lattice further. Then silicon ingot is slowly cooled to room temperature. Cooling rate cannot exceed 50 degrees Celsius per hour. Both ends of silicon ingot are cut off because crystal quality in these sections is typically inadequate. After cutting, silicon ingot length is approximately 1.5 meters with diameter of 300 millimeters. This silicon ingot will be sliced into hundreds of thin wafers. Silicon ingot needs slicing into thin pieces. These pieces are wafers. Slicing uses inner diameter saw. This equipment uses extremely thin metal ring blade. Blade inner diameter is 310 millimeters, outer diameter 350 millimeters, thickness only 0.1 millimeters. Blade is manufactured from stainless steel with edge embedded with diamond particles. Diamond particle diameter is 30 micrometers, uniformly distributed on blade edge. Diamond is nature's hardest substance with hardness reaching Mohs scale 10, the only choice for cutting hard brittle material like silicon. During cutting, blade rotates at 3,000 revolutions per minute. Silicon ingot is secured in precision fixture. Fixture advances silicon ingot through blade at 0.1 millimeters per second. This speed is extremely slow. Cutting one wafer requires approximately 15 minutes. Cutting process generates substantial heat. To avoid heat damaging silicon crystal, coolant must be used. Coolant is mixture of pure water and ethylene glycol with temperature maintained at 10 degrees Celsius. Coolant flows at 20 liters per minute, flushing cutting zone, removing heat and silicon powder. Each cut yields wafer thickness of 775 micrometers, approximately equivalent to 8 A4 paper sheets thickness. But because blade itself has thickness, each cut loses approximately 100 micrometers silicon material. This is called kerf loss, unavoidable waste in wafer manufacturing. 1.5 meter long silicon ingot can be sliced into approximately 2,000 wafers. But these wafers' quality is not completely uniform. Wafers near ingot ends typically have inferior quality. Middle section wafers have best quality. Therefore, wafers ultimately usable for chip manufacturing are approximately only 1,500 pieces. Cut wafer edges are very sharp, potentially causing injury or generating fragments in subsequent processes. Therefore, edge chamfering treatment is required. Chamfering uses specialized grinding tool grinding wafer edge into arc shape with arc radius approximately 0.2 millimeters. After chamfering, wafer surface is still rough, covered with saw marks left from cutting. These saw marks' depth is approximately 5 micrometers, requiring removal through polishing. Polishing divides into rough polishing and fine polishing, 2 stages using different particle size slurries. Rough polishing slurry contains aluminum oxide particles with diameter of 1 micrometer. Polishing wheel rotates at 1,000 revolutions per minute, applying pressure on wafer of 0.5 newtons per square centimeter. Rough polishing can remove most saw marks, reducing surface roughness to 0.5 micrometers. Fine polishing uses finer slurry containing silicon dioxide particles with diameter of 0.05 micrometers. Fine polishing pressure is lighter at 0.2 newtons per square centimeter. After fine polishing, wafer surface roughness can reduce to 0.001 micrometers, specifically 1 nanometer. Such surface appears mirror smooth under microscope. Polished wafers require thorough cleaning. Cleaning uses ultra-pure water with water resistivity reaching 18.2 megohm centimeters, highest purity water can achieve. Cleaning process includes chemical cleaning and ultrasonic cleaning with duration of 30 minutes. After cleaning, wafer surface cannot have any residual particles or chemical substances. Cleaned wafers undergo quality inspection under microscope. Inspection content includes surface defects, thickness uniformity, flatness, and others. Only wafers passing all inspections can proceed to next process. Unqualified wafers are downgraded for lower requirement applications or directly scrapped. Cleaned wafers enter oxidation furnace. Oxidation is one of most fundamental and important processes in chip manufacturing. Growing silicon dioxide layer on silicon surface achieves multiple functions including insulation, protection, and pattern transfer. Oxidation furnace is quartz tube several meters long with internal temperature reaching 1100 degrees Celsius. Wafers are vertically placed on quartz boat. Each quartz boat can accommodate 100 wafers with spacing of 10 millimeters between wafers. Oxidation process divides into dry oxidation and wet oxidation. Dry oxidation uses pure oxygen with oxygen flow rate of 5 liters per minute. Wet oxidation adds water vapor to oxygen with water vapor partial pressure approximately 0.5 atmospheres. Wet oxidation speed is approximately 10 times faster than dry oxidation, but grown oxide layer quality is slightly inferior. This time we use dry oxidation process. Wafers are exposed to pure oxygen in 1000 degrees Celsius environment. Silicon atoms chemically react with oxygen molecules generating silicon dioxide. Reaction equation is C plus O2 CO2. This reaction occurs on silicon surface. Oxide layer grows gradually from nothing. Oxide layer growth rate decreases over time. Initial few minutes, growth rate is approximately 1 nanometer per minute. But as oxide layer thickens, oxygen molecules must penetrate already formed oxide layer to reach silicon surface. Speed gradually decreases. Growing 100 nanometer thick oxide layer requires approximately 6 hours. Oxide layer thickness is measured through ellipsometer. Ellipsometer emits polarized light to wafer surface. Analyzing reflected light polarization state changes precisely calculates oxide layer thickness. Measurement precision reaches 0.1 nanometers. Oxide layer uniformity is crucial. Across entire wafer, oxide layer thickness variation must be controlled within plus or minus 2%. This requires oxidation furnace internal temperature distribution to be extremely uniform. Temperature fluctuation cannot exceed plus or minus 1 degree Celsius. To achieve this requirement, oxidation furnace uses multi-zone heating system. Each zone temperature is independently controlled. After oxidation completion, wafers require slow cooling inside furnace. Cooling rate is controlled at 5 degrees Celsius per minute. Cooling from 1000 degrees Celsius to 400 degrees Celsius requires 2 hours. During cooling process, nitrogen atmosphere is maintained preventing surface contamination. When temperature drops below 400 degrees Celsius, wafers can be removed. Wafer surface after oxide layer growth presents pale coloration. This is light interference effect. Different thickness oxide layers present different colors. 100 nanometer thick oxide layer typically presents pale purple. 200 nanometers presents blue-green. Observing color, experienced engineers can roughly judge oxide layer thickness. This thin silicon dioxide layer, though only 100 nanometers thick, possesses excellent insulation properties. Its breakdown voltage reaches 10 million volts per centimeter, effectively isolating different conductive layers. Simultaneously, silicon dioxide chemical stability is also good, protecting underlying silicon from corrosion. After oxide layer growth completion, next step is photolithography process. Photolithography is most critical process in chip manufacturing, determining chip's minimum feature size. Before photolithography, first photoresist layer must be coated on wafer surface. Photoresist is light-sensitive organic polymer. After exposure, photoresist chemical structure changes and solubility also changes. According to solubility change after exposure, photoresist divides into positive resist and negative resist. Positive resist solubility increases after exposure. Negative resist solubility decreases after exposure. This time we use positive resist. Resist coating occurs in automatic coater. Wafer is first placed on vacuum chuck. Chuck firmly holds wafer through negative pressure. Then chuck begins rotating. Rotation speed gradually accelerates from 0 to 3000 revolutions per minute. When rotation speed reaches 1000 revolutions, coating nozzle moves above wafer center, beginning to dispense photoresist. Photoresist viscosity is approximately 10 centipoise, equivalent to 10 times water. Dispensing amount is 3 milliliters, forming droplet approximately 20 millimeters diameter at wafer center. As wafer continues accelerating rotation, centrifugal force flings photoresist outward. Photoresist rapidly spreads across wafer surface, forming uniform thin layer. Faster rotation speed produces thinner photoresist layer. At final rotation speed of 3000 revolutions per minute, photoresist thickness is approximately 1 micrometer. Spin coating lasts 60 seconds. During this process, most photoresist is flung beyond wafer edge. Actually remaining on wafer is only approximately 5%. This appears wasteful, but spin coating is currently most effective method for obtaining uniform thin film. After spin coating, photoresist still contains substantial solvent, requiring removal through baking. Baking occurs on hot plate with hot plate temperature set at 110 degrees Celsius. Wafer rests on hot plate for 90 seconds. Solvent gradually evaporates. Photoresist becomes hard. Baking temperature and time control is very strict. Excessive temperature or excessive duration causes photoresist over cross-linking, affecting subsequent exposure and development. Insufficient temperature or insufficient duration causes incomplete solvent removal, also affecting photolithography quality. Temperature control precision is plus or minus 0.5 degrees Celsius. Time control precision is plus or minus 1 second. After baking, photoresist thickness slightly decreases from 1 micrometer to approximately 0.9 micrometers. This is because after solvent evaporation, photoresist volume shrinks. Thickness uniformity is checked through optical thickness gauge. Thickness variation across entire wafer must be within plus or minus 1%. Photoresist surface requires absolute cleanliness. Even 0.1 micrometer diameter particle produces shadow during exposure, causing pattern defect. Therefore, entire coating process occurs in cleanroom. Particles above 0.1 micrometers per cubic meter of air do not exceed 10 particles. This is ISO Class 1 cleanliness standard. Wafers coated with photoresist are placed in dedicated wafer carrier filled with nitrogen, preventing photoresist oxidation or contamination. After wafer carrier is sealed, it is sent to photolithography machine through automatic transport system. Throughout entire process, wafers are never exposed to ordinary air. Photolithography machine is most expensive equipment in wafer fab. One advanced photolithography machine costs over $100 million. Its function is precisely transferring chip design pattern onto photoresist. Wafer is placed on precision stage. Stage can move in X, Y, Z 3 directions with positioning precision reaching 1 nanometer. This equals positioning precision reaching 10,000th of hair thickness across football field size range. Photolithography uses deep ultraviolet light with wavelength of 193 nanometers. This light has high energy capable of triggering photoresist chemical reactions. Light source is excimer laser using argon fluoride gas to generate laser. Laser output power is 60 watts, but after passing through optical system, power reaching wafer is only approximately 10 watts. Reticle is photolithography key. Reticle is quartz glass plate with chip pattern etched using chromium metal. Chromium layer thickness is approximately 80 nanometers, completely blocking ultraviolet light. Reticle manufacturing precision is extremely high. Pattern position error cannot exceed 2 nanometers. After light passes through reticle, it focuses onto wafer surface through complex optical system. Optical system includes dozens of precision lenses with total value possibly reaching tens of millions of dollars. These lenses are manufactured from fused silica with surface polishing precision reaching 0.1 nanometers, almost atomic level smoothness. Optical system projects reticle pattern onto wafer with 4 times reduction. This means 1 micrometer feature on reticle becomes 0.25 micrometers on wafer, specifically 250 nanometers. Through this reduction projection, reticle manufacturing difficulty can be reduced. Exposure is not completed once but adopts step and repeat exposure method. Each exposure covers approximately 600 square millimeters area on wafer called one exposure field. Then stage moves to next position for next exposure. One 300 mm wafer has approximately 100 exposure fields. Each exposure field exposure time is approximately 0.5 seconds. But including stage movement, alignment, focusing and other steps, processing one exposure field requires approximately 5 seconds. Therefore, completing one wafer exposure requires approximately 8 minutes. Alignment is critical step before exposure. Wafer already has alignment marks formed from previous process steps. Photolithography machine identifies these marks, ensuring new pattern precisely aligns with old pattern. Alignment precision requirement reaches 3 nanometers, requiring extremely complex image recognition algorithms and precision mechanical systems. During exposure process, environmental stability is crucial. Room where photolithography machine is located has temperature controlled at 22 degrees Celsius with fluctuation not exceeding plus or minus 0.01 degrees Celsius. Humidity controlled at 45% with fluctuation not exceeding plus or minus 1%. Air pressure, vibration, air cleanliness all have strict requirements. After exposure completion, Exposed and unexposed regions in photoresist already have different chemical properties but no visible change from appearance. Subsequent development process is required to reveal pattern. After exposure, wafer requires development to reveal pattern. Developer is alkaline solution typically using tetramethylammonium hydroxide with concentration of 2.38%. This concentration is carefully formulated to effectively dissolve exposed photoresist areas without corroding unexposed areas. Development occurs in automatic developer. Wafer is secured on rotating platform. Developer sprays from nozzle uniformly covering entire wafer surface. Developer flow rate is 50 milliliters per second with temperature maintained at 23 degrees Celsius. Temperature control is important. For each degree temperature increase, development rate increases approximately 7%. Development time is typically 60 seconds. During these 60 seconds, exposed photoresist areas gradually dissolve entering developer solution. Unexposed photoresist areas remain unchanged. Development process can be observed real-time through optical monitoring system. When photoresist reflectivity reaches specific value, development completion is indicated. After development completion, immediate rinse with deionized water is required, stopping development reaction. Rinse water flow rate is 100 milliliters per second with rinse time of 30 seconds. After rinsing, high purity nitrogen dries wafer. Nitrogen pressure is 0.3 megapascals with drying time of 60 seconds. On developed wafer, photoresist forms precise pattern. Exposed area photoresist is completely removed, exposing underlying oxide layer. Unexposed area photoresist remains, forming protective layer. This pattern is precise replica of reticle design pattern. Pattern critical dimension requires measurement through scanning electron microscope. Critical dimension refers to smallest feature size in pattern. For advanced processes, this dimension may be only tens of nanometers. Measurement precision requirement reaches 0.1 nanometers, requiring electron beam scanning in high vacuum environment. Development quality inspection also includes pattern sidewall angle. Ideal sidewall should approach vertical with angle of 85 to 90 degrees. If angle is too small, development is insufficient with photoresist residue at pattern bottom. If angle is excessive or even undercut occurs, development is excessive. If problems are discovered after development, entire photolithography process requires restarting. First, specialized stripper completely removes photoresist. Then recleaning, recoating, re-exposure, redevelopment. This rework process increases cost and time. Therefore, every step must be strictly controlled, avoiding rework. Development qualified wafers proceed to next process, etching. Photoresist pattern serves as mask, protecting underlying areas not requiring etching. Areas without photoresist protection have oxide layer etched away, exposing silicon substrate. Etching is process of transferring photoresist pattern to underlying material. Modern chip manufacturing primarily uses plasma etching. This method has high precision, good controllability, capable of etching vertical sidewalls. Etching occurs in vacuum chamber. Wafer is placed on electrode powered by RF power supply. Electrode is also called chuck. Vacuum pump evacuates chamber, reducing pressure below 0.01 pascals. Then etching gas is introduced. For silicon oxide etching, carbon tetrafluoride gas is used with flow rate of 100 milliliters per minute. RF power supply frequency is 13.56 MHz with power of 1000 watts. High-frequency electric field ionizes gas molecules, forming plasma. Plasma emits blue-purple glow resulting from ionized fluorine and carbon atoms emitting light. Fluorine atoms and plasma possess high chemical reactivity capable of reacting with silicon dioxide. Reaction equation is CO2 plus 4FCF4 plus O2. Generated silicon tetrafluoride is gas evacuated by vacuum pump. Thus, oxide layer is gradually etched away. Etching rate is approximately 200 nanometers per minute. Etching 100 nanometer thick oxide layer requires 30 seconds. One important characteristic of plasma etching is anisotropy. This means etching primarily proceeds vertically with minimal lateral etching. This is because ions in plasma gain kinetic energy under electric field action, vertically bombarding wafer surface. This directional bombardment makes etched pattern sidewalls approach vertical with sidewall angle reaching 88 to 90 degrees. Etching selectivity is also important. Selectivity refers to etching rate ratio. For silicon oxide etching, we desire fast oxide layer etching rate but slow photoresist and silicon substrate etching rates. Ideal selectivity is silicon oxide to photoresist selectivity of 5 to 1, silicon oxide to silicon selectivity of 100 to 1. Etching endpoint detection is achieved through optical emission spectrometer. When etching reaches silicon substrate, plasma emission spectrum changes. Spectrometer real-time monitors specific wavelength light intensity. When sudden light intensity change is detected, etching immediately stops. Endpoint detection response time is less than 0.1 seconds. After etching completion, ashing treatment is required, removing residual photoresist. Ashing uses oxygen plasma. Oxygen atoms oxidize organic photoresist into carbon dioxide and water. These products are gases evacuated. Ashing time is approximately 2 minutes. After ashing, wafer surface only has oxide layer with etched pattern. Through scanning electron microscope inspection, three-dimensional structures formed by oxide layer are visible. These structure dimensions may be only tens of nanometers, but with sharp edges, smooth surfaces, no residues. This etched pattern is future chip prototype. Subsequent processes continue on this foundation, depositing conductive layers, re-photolithography, re-etching, repeating dozens of times, ultimately forming complete chip containing billions of transistors. After etching completion, wafer surface has raised and recessed pattern. Next, new material layer must be deposited on surface. This time we deposit polysilicon serving as transistor gate material. Deposition occurs in chemical vapor deposition furnace. This is sealed quartz tube approximately 2 meters long with inner diameter of 200 millimeters. Wafers are vertically placed on quartz boat. Quartz boat is pushed into furnace tube center region. Furnace tube is heated to 620 degrees Celsius. This temperature is carefully selected. sufficiently high to decompose precursor gas yet not excessive, causing damage to wafer existing structures. Temperature variation along furnace tube length does not exceed plus or minus 2 degrees Celsius, ensuring uniform heating of all wafers. Precursor gas is silane with chemical formula CH4. Silane is colorless gas but extremely flammable, spontaneously combusting upon air contact. Therefore, delivery system must be completely sealed, preventing leakage. Silane flow rate is 50 milliliters per minute. Carrier gas is hydrogen with flow rate of 2 liters per minute. At high temperature, silane decomposes CH4C plus 2H2. Decomposed silicon atoms deposit on wafer surface. Hydrogen is exhausted outside furnace. Deposition rate is approximately 10 nanometers per minute. Depositing 100 nanometer thick polysilicon layer requires 10 minutes. Deposited polysilicon comprises numerous tiny grains. Each grain size is approximately 50 nanometers. Between grains are grain boundaries with irregular atomic arrangement. Polysilicon resistivity is approximately 1000 ohms per centimeter. Much higher than monocrystalline silicon but sufficient for gate material. After deposition completion, polysilicon requires doping treatment to reduce resistivity. Doping occurs in ion implanter. Phosphorus ions are accelerated to tens of kiloelectronvolts energy, bombarding polysilicon surface. Phosphorus ions embed into silicon lattice, providing free electrons, reducing resistivity below 1 ohm per centimeter. Ion implantation dose is 5 times 10 to 15th power ions per square centimeter. Implantation energy is 20 kiloelectronvolts. At this energy, phosphorus ions can penetrate approximately 50 nanometer depth, precisely covering entire polysilicon layer thickness. Implanted wafers require annealing, activating dopant atoms. Annealing occurs in rapid thermal processing furnace reaching 1000 degrees Celsius but lasting only 10 seconds. Rapid heating and cooling can activate doping while avoiding impurity diffusion. After annealing, polysilicon appears gray with slightly rough surface. But this does not affect its function. It will be patterned in subsequent processes, forming transistor gates. Polysilicon thickness, uniformity, doping concentration all undergo precision measurement, ensuring design requirement compliance. This 100 nanometer thick polysilicon layer, though appearing insignificant, is key to chip functionality. It controls transistor switching, determining current flow. Billions of such transistors working cooperatively realize all computer functions. After multiple cycles of photolithography, etching and deposition, wafer has formed billions of transistors. But these transistors are still isolated, requiring connection through metal wires, forming complete circuit. This process is called metallization. Metallization material is aluminum-copper alloy containing approximately 0.5% copper. Pure aluminum has low resistivity but insufficient mechanical strength, prone to electromigration failure. Adding small amount of copper can increase strength, extending wire lifespan. Metal deposition uses physical vapor deposition, also called sputtering. In vacuum chamber, aluminum-copper alloy target is bombarded by high-energy argon ions. Target surface atoms are knocked out, depositing onto wafer surface. Sputtering vacuum is 0.001 pascals. Argon flow rate is 50 milliliters per minute. Sputtering power is 5,000 watts with deposition rate approximately 50 nanometers per minute. Depositing 500 nanometer thick metal layer requires 10 minutes. Deposited metal layer uniformly covers wafer surface, filling all raised and recessed structures. After metal deposition, wire pattern formation requires photolithography and etching. Metal etching uses chlorine-based plasma with etching rate approximately 300 nanometers per minute. Etched wire width may be only 100 nanometers with spacing also 100 nanometers. In 1 square millimeter area, tens of thousands of such wires may exist. Wires are isolated by silicon dioxide. Isolation layer forms through chemical vapor deposition with thickness approximately 500 nanometers. After deposition, chemical-mechanical polishing is required, flattening surface. Polishing uses slurry containing silicon dioxide particles on rotating polishing pad. After polishing, surface flatness requirement is high. Height difference cannot exceed 5 nanometers. This is because subsequent second metal layer deposition is required above. Modern chips typically have 8 to 10 metal layers. Layers connect through vias. Adding each metal layer requires repeating deposition, photolithography, etching, polishing processes. Final metal layer is called aluminum pad with thickness reaching 1 micrometer, much thicker than other metal layers. Aluminum pad is chipped to external world connection interface. Wire bonding occurs on aluminum pads. Aluminum pad surface requires special treatment, typically plating nickel and gold layer, preventing oxidation, improving solderability. After metallization completion, chip circuit portion is completely finished. Viewed from above, intricate metal wire network is visible, resembling city streets. These wires connect billions of transistors, transmitting weak but precise electrical signals, realizing complex logical operations. After chip manufacturing completion, testing is required, confirming which chips are good and which are bad. Testing occurs when wafer has not been diced into individual chips, called wafer-level testing. Testing occurs on automatic probe station. Probe station has precision vacuum chuck securing wafer and stage movable in X, Y directions. Stage positioning precision reaches 1 micrometer, accurately moving each chip below probes. Probe card is testing key component. It is printed circuit board with hundreds of extremely thin probes installed. Each probe diameter is only 25 micrometers. Tip is finer, only 5 micrometers. Probes are manufactured from beryllium copper alloy, possessing good elasticity and conductivity. During testing, probe card descends. Probes contact chip surface aluminum pads. Contact force is controlled at approximately 5 grams per probe. Insufficient force causes poor contact. Excessive force may damage aluminum pads. Probes slightly scrub aluminum pad surface, scratching through surface oxide layer, establishing good electrical contact. Test program is stored in computer containing thousands of test items. First, power supply current is tested, confirming chip has no short circuit. Then various functional modules are tested, inputting specific test vectors, checking whether outputs are correct. Each chip testing time is approximately 2 seconds. Test results divide into several grades. Chips completely passing all tests are marked as premium grade. Chips with some abnormal functions but normal main functions may be marked as acceptable grade for lower requirement applications. Completely non-functional chips are marked as scrap. During testing process, computer generates wafer map marking each chip test result with different colors. Through wafer map, yield distribution is intuitively visible. If chips in MO region fail concentratedly, that region may have experienced contamination or process abnormality during manufacturing. One wafer may have several hundred chips but not all can qualify. Even with good process control, yield can only reach 70 to 90%. Many factors affect yield including particle contamination, equipment failure, process variation. Improving yield is Wafer Fab eternal pursuit. After testing completion, wafers are sent to dicing process. Diamond blade cuts along scribe lines between chips dividing wafer into individual chips. Good chips are selected for packaging testing. Bad chips are discarded. From silicon ingot to finished chips, entire process may last several months experiencing hundreds of processes. Every process requires extremely high precision and cleanliness. Even one tiny mistake may cause entire wafer batch scrap. This is why semiconductor manufacturing is called one of humanity's most complex manufacturing processes. And our journey slowly approaches conclusion in this precision testing. From regular arrangement of silicon atoms to collaborative operation of billions of transistors, we witnessed crystallization of human wisdom. Now let these precision processes accompany you into peaceful dreams. Good night.
gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark.